This is the first day of our quadratics unit, and we're just going to go through a couple of review points from grade 10. So hopefully you can identify that this here has been given to you in vertex form, and when it says to state the optimal value, I'm hoping that you also remember that the optimal value of a quadratic function is the maximum or the minimum. And so in order to reach the maximum or the minimum, first we have to look and see, is this function opening up or down? So that means we need to look at the a value. And my a value is -2, which means that my function is opening down. That means that I'm going to have a maximum value. And then the maximum value is how high or low it's going to go. So its maximum value is how high it's going to go, not higher than. And the minimum value would be it's not going to be lower than. So the optimal value of this equation is going to be y equals -3, because this is the y value of my vertex, and the vertex in this case is -1, -3. And so the optimal value of this function is y equals -3. Now we threw some fractions in here just to throw you off. Same question, what is the optimal value? Start with the a value. This a value is positive. That means that my quadratic is pointing up. And so that means that the minimum, this is going to have a minimum, and the minimum value is going to be +5. So my optimal value for this function is y equals +5. So there are those two graphs sketched. Very much just a sketch, especially my graph on the right. My vertex didn't come out very nicely. But do note as well that neither of these graphs are going to cross the x-axis, so these equations in standard form would not be factorable. So now just a reminder of how to factor a perfect square. If you recall, a perfect square is of a consistent format, and that generic format is ax squared plus or minus 2abx plus b squared. And so what we do to factor a perfect square is we take the square root of the a, which in this case is 1x squared, so the square root of that would be x, and then we take the square root of our final value here, which in this case would be my b squared, which is 3, and then the sign here drives the sign in my bracket. And when we use that format, it's really easy also to identify when you have a perfect square. When you've got perfect squares on either end of your trinomial, surrounded by a term that is the square root of both of those times 2, right? Because the square root of x squared is x, and the square root of 25 is 5, and then 5 times 2 is 10, and that gives you your middle term. So, oops, sorry about that. Hopefully you can see that these are very easy to factor. And I'm just going to leave that one like that. And this is going to be x plus 6 squared. Now that little factoring review was to remind you that in order for there to be a perfect square, my second term in the bracket has to be the same. And so when we complete the square, what we do is we basically fudge that. So in this case, remember that we're going to factor the 2 out of the first two terms. Leave the -7 over there. And so now you're saying, okay, so I need an x squared, and I've got this term here has to be shared between two different places. Because remembering that a perfect square has x squared plus or minus 2abx plus b squared. So this is my abx term, or my 2abx term, which means that this 4 has to be divisible by 2 in order to give me a perfect square. And this is where that fudge factor comes in. So now we have, sorry, my things are getting together just a little bit. So remember, when we're completing the square, I'm not changing the equation, I'm just reorganizing it. So over here, when I'm looking to get my perfect square, I have to do -2 times -2, which is going to give me +4. And So I'm going to add that to my bracket, but because I can't change my equation, whatever I add inside the bracket, I have to remove outside the bracket. So now I can factor my bracket and collect the like terms that are outside the bracket. Remembering that, I have to multiply that -4 that I added here, subtracted here, but that has an a value outside the bracket, so I have to multiply that -4 by that a value in order to be removing everything that I added to the equation. And there is my completed square, y equals 2 bracket x minus 2 squared minus 15. So we'll just do the same series of steps for this second example. So we have to share that 2x in this equation here between these two boxes, and 2x shared two ways is just 1x in each one, which is going to give me outside of the square my positive ones, and 1 times 1 is 1. So that's what I'm going to have to add to my bracket and then also subtract outside of my bracket in order to force this into a perfect square. So now that I have my perfect square bracket, I can factor that perfect square and collect my like terms that are outside the bracket, and then I will have completed the square. So now the vertex of this completed square, or the vertex for this equation here, is -1, -13. My optimal value, it is a minimum of y equals -13. The vertex on this is 2, -15 with an optimal value of y equals -15. So the second part of the lesson today is about radicals. Rational numbers are numbers that can be written in fraction form or in a over b form. Irrational numbers cannot be written as a simple fraction. These are certain numbers that are non-terminating and non-repeating decimals, like pi, like some radicals, like some trig ratios. And so what we'll need to do is talk about so these numbers, tend to be called radicals. Things like pi, things under square root signs that don't terminate in a round number or a terminal decimal or a periodic decimal. So there are certain elements to radicals. One of those elements is the radicand, and the radicand is what is under the root sign. So it doesn't have to be a square root. The index, as indicated here, is the number of roots that we're taking. So it doesn't have to be a square root, because a square root, we usually leave that index off because we're presuming that if we have it off, that the number there is a 2, and so it's just the square root. So what's the number underneath that times itself that gets you that number? See here we've got a cube root, this one's a fourth root. The index tells you the number of times the number has to multiply by itself to get to that radicand. The radical is the radical sign, right here. The radicand, like I said, is what's underneath, and then the index is how many times you're taking the root. So the entire radical includes the radicand, the radical, and the index. And a pure radical has everything underneath the radical sign. Like we have here. A mixed radical has some of the radical under the radical sign and some of the radical, or some of the number, outside the radical sign. Or the radical is multiplied by a number. So we can take an entire radical and change it to a mixed radical as long as there is a perfect square or a perfect root that you were looking for underneath the radical sign. So we're going to have a look at a couple of these entire radicals and change them to mixed radicals by looking for the perfect square factor that is in the radicand. So think about the square root of 24. So the square root of 24, I can simplify that by saying, okay, so the square root of 24 has a factor of 4 in there, and 4 is something that can be square rooted evenly. So I can change an entire radical into two subradicals multiplied by each other. So we say, all right, so the square root of 24 is the same as the square root of 4 times the square root of 6, but I know that the square root of 4 is... So I can simplify that square root of 24 into 2 times the square root of 6. Now let's look at 98. So when you look for perfect squares in the square root of 98, we've got it's 49 times 2, and we know the square root of 49 is 7. So we can simplify that into 7 times the root of 2. Square root of 50, hopefully that's easy to identify, that's square root of 25 in the square root of 2. And the perfect square hiding under root 180 is the square root of 36 times square root of 5. So as a mixed radical, square root of 180 is the same as 6 times the square root of 5. So last but not least, we're going to look at the 4 different ways, except we're not going to be using our graphing calculators. Remember that the best graphing calculator out there, usually available on your phone, it's the app called Desmos. It is a fantastic app for at least checking your work. I really don't suggest you use it as a tool to actually do your work. It's a great tool to check your work. I'm just giving you a heads up because I can tell when you've used Desmos most of the time because there's usually key points missing off of your graph. So don't use it as a way to cheat. Use it as a way to check your work. So we're going to solve this quadratic using these 3 different methods. So the first way we're going to use is factoring. So we always common factor out the 2 first, and then our 2 factors that are going to multiply to -7 and add to -6 are -7 and +1. So now our zeros, remember we take each of these brackets and set them equal to 0 to find the zeros. So by factoring, we say that x equals 7 and x equals -1, or the 2 points -1, 0, and 7, 0 are the solutions, also as known as the roots, also known as the zeros. All of these things here all mean the same thing. That is where it's going to cross the x-axis. So using the quadratic formula, we don't have to factor to use the quadratic formula. So hopefully we'll remember that that is the quadratic formula. In this case, so now we've got x equals 12 plus 16 over 4, which is the same as 28 over 4, which is 7, or 12 minus 16 over 4, which is -4 over 4, or -1. And so now we have our zeros from the quadratic formula. The last way we can solve a quadratic equation, of course, is by completing the square. So following the steps that we reviewed on the last page, we'll just factor that 2 out of the first 2 terms. Half of 6 is 3, and 3 squared is 9, so that's what we need to use to complete our square. Now we can factor our bracket and collect our like terms. So negative 18 subtract 14 is negative 32. So now we just need to rearrange this equation and solve for x. So of course now we're just trying to get x by itself, so we'll move the 32 over, we'll divide both sides by 2. Now this is just solving for x, like any normal solving equation. Next thing is to take the square root of both sides. And remember, when I take the square root of a number, I'm going to have plus or minus solutions. So now we're going to have 2 different solutions to this. So there's our 2 different zeros once again, this time by completing the square. So I'm going to leave my therefore statement because we just solved the same answer 3 different ways. So the last thing that we're going to review today is how to simplify a polynomial, which means that we're going to multiply out our brackets. So here's where I'm going to show you guys the area model. Most of you would be familiar with the rainbow method. However, based on the last quiz that we had, I need to remind a lot of you how to FOIL properly. So, as you can see, this new area model, I've just got the one bracket here and the other bracket here, and I'm just using a grid to help keep track of what it is that I need to multiply out. And then as you can see, the diagonal contains my like terms. And so I just have to add up those like terms, and I've got my bracket, which now I will have to multiply through by 2 because I only made one box and I have 2 of them. And so there's that polynomial expanded. We're going to do one more, which has a factor of 3, so I'd be technically making 3 boxes instead of 2. So I take one of the brackets, I'll take this one and put it on the top, take the second bracket and put it on the side. Now the signs are very important, so make sure that they stay with the coefficients. And now I'm just going to multiply each row by each column. So when I multiply each row by each column, I can fill up the squares in my box. And now this is where the area model comes in, because I have to add each of these boxes up to figure out what the area of my square is. And that is going to give me 2x squared minus x minus 3, which I'm then going to multiply by 3 because I have 3 of these boxes. And there is that expanded polynomial. I've written this line in here. Sorry, that plus 1 does not go with that equation. That went with the box. Is at the same as if I FOILed it out and used x times 2x, x times negative 3, 1 times 2, and 1 times negative 3. I would still, regardless of how I did it, I'm still going to get that bracket right there. And then I'm going to multiply that bracket by 3 to get my final term. So here are a couple of factoring examples of things that should be easy to that you can identify. So anytime I have a perfect square and a perfect square separated by a negative, I should immediately know that that is a difference of squares. And so when I have a difference of squares, I square root the first term, which 25x squared square rooted is 5x. I square root the second term, which 100 square rooted is 10. I put that into both of my brackets, and the only thing that's different is the sign. So I'm going to put a negative in one bracket and a positive in the other, and that is the difference of squared factored. So when I come over here and you say to me, oh my goodness, Miss Lacombe, what are you trying to get us to do? Look at those nasty, horrible numbers. You need to look at them and identify that 49x squared is a perfect square, positive 1 is a perfect square, and the square root of 49 is 7, and the square root of 1 is 1, and 7 times 1 times 2 is 14, which means that this is a perfect square. And so now all you have to do to factor that is take the square root of the first, the square root of the last, and then that sign drives the sign in the bracket, and it's squared. And that is a factored perfect square. Last but not least, we have a complex trinomial. First thing you have to look at, is there anything common in this equation? And yes, there is. It has a common factor of 2. So we're going to common factor out the 2 before we go ahead and do the complex trinomial factoring. So now you can use the complex trinomial factoring of your choice. My favorite, my personal favorite, is the Australian method. So we're going to be looking at, are there any terms that are going to multiply to positive 15 and add to negative 9? And the answer to that, of course, is no. So that is as far as I can go on this factoring. So that's it for the lesson for today. Please go to the review of adding, subtracting, and multiplying polynomials worksheet that is attached with today's lesson.